Hi, and welcome to this first in a series on stationary points to do with differentiation. Now, this is the second set of videos on differentiation, so if you're not quite sure what differentiation is, you need to go back and check out the first series. But if you can't do differentiation, you know how to use differentiation to find gradients on curves, then you're good to go and we can proceed onwards. So, this set of videos, we're going to be looking at how to find what we call stationary points and identifying different types of stationary points. Once we've found them, using something called a second derivative to determine exactly what kind of stationary point you're looking at. And then we're going to move on from there and look at stationary points and curve sketching. We've already done a bit of work on curve sketching, which is going to give you some more tools to be able to do that job. And finally, looking at how we can solve practical problems using differentiation involving maximization and minimization problems. So, this first video, we're looking at just how to locate a stationary point, what a stationary point is, and to determine the characteristics of that stationary point. So, if we're ready, let's crack on. Right, stationary points. You spend a lot of time at A-level maths kind of figuring out where stationary points are on curves, and essentially they're stationary points called turning points. They're basically where a curve stops going up and starts going back down again, for example. So you could get a maximum point, you could get a minimum point, or you could get what's referred to as a point of inflection. So let's have a look at a curve and see what these things look like. So there's a very bizarre and complex curve. I think that's actually a power 4 curve? Power 5 curve. And what we've got is different key points on here. So what we've got is our maximum point, or we might refer to as a local maximum, say where it stops going up and starts coming back down again. Clearly our minimum point is going to be the reverse of that, when it stops going down, starts going back up again. And the point of inflection is that one in the middle there, where the curve flattens out. And the key thing that all these things have got in common is that they all have a gradient of 0 at those points. So what we're saying is dy dx, the gradient at those points, is 0. And if we know the gradient is 0, and you've seen from previous videos, we'll be able to figure out where those points are. So let's have a look. We've got stationary points on that curve there. So we've got 5 plus 6x minus 3 over 2x squared minus x cubed. Where are the stationary points? So here we go. So we'll start by differentiating. So there's the differentiated version, the gradient function. And we know that the stationary points occur when dy dx is 0. So we're going to put that into our equation. So dy dx, this thing here, that's going to have a value of 0. So let's put that in there. So now we've just got a quadratic equation to solve, and in this particular instance you'll notice that each of the terms is divisible by 3, so we can divide the whole equation by 3 and we end up with that. And then all we've got to do is solve that, and I'm fairly sure we're going to be able to factorise that. There it is. So that gives us values of x is minus 2 and x is 1. Now the question is saying, okay, where are the coordinates of the stationary points? So if we want the coordinates of those points, we've got the x coordinates. We're going to need to find the y coordinates. So when x equals minus 2, we've got to go back to this one up here, stick x is minus 2 into there, and we're going to get y is minus 5. And likewise, when x is 1, y is 9. And so there you go, there's our two coordinates where we have stationary points on this particular curve. Now, if we drew the curve, that's what it looks like. So those are our two stationary points, and you can see we've got minus 2, 5 is a minimum, and 1, 9 is a maximum. But the key thing is, like, well, how are we going to figure out which one is a maximum, which one is a minimum, without having to draw the curve? Because obviously drawing the curve is not entirely straightforward. Yes, we've got a negative cubic, but it's not immediately obvious what's going on just from the information we had previously. Obviously I did this diagram using a piece of graphing software. So how can we figure out that this one is a minimum and that one's a maximum without having to draw the curve? So let's have a look at what's going on. So there's our curve that we had before from from the previous slide. And if we just have a look at that minimum point, and what I'm going to do is just kind of zoom in on that a little bit, and there it is. And if we have a look at what's going on with that curve, well, the gradient, if we have a look just slightly to the left of minus 2, so I'm going to say, well, at this point here, all along here, we have got a negative gradient, so dy dx is negative. We know that at our minimum point here, when x is minus 2, the gradient is 0. And we know that if we go after i.e. x is greater than 2, we've got a positive gradient. And if you look at what's happening, the gradient has gone from negative to 0 to positive, which means effectively as x has increased, as we've gone from x being negative through -2 and then beyond -2 towards the positives, we can see that the gradient of the curve is increasing. So it's gone from negative to 0 to positive. The gradient is getting bigger, effectively. If we have a look at the maximum point, do exactly the same thing. There's my maximum, and this time it's happening around 1, and here we've got where x is less than 1. Okay, the gradient is positive. When x is equal to 1, the gradient is 0, and when x is greater than 1, it's negative. So what's happening here is the gradient has gone from positive through 0 down to the negative, so the gradient is decreasing all the way along as we go around that point. So what we're saying is for a minimum point, the gradient is increasing, and for a maximum point, the gradient is actually decreasing. So what we're looking at really there is kind of how the gradient is changing, and if the gradient is the rate of change, we're looking at technically what's effectively the rate of change of the rate of change, at which point your brain's starting to smoke a little bit getting your head around it, but I'm sure you can figure it out. And this thing, the rate of change of the rate of change, is called the second derivative, and we've got this funny notation here where you've got d squared y over dx squared. So that means basically what we're going to do is differentiate and then differentiate for a second time. Now, being as if we go around a minimum point, the gradient is increasing, the rate of change of the gradient will be positive because the gradient is getting bigger. So for a minimum point, we've got the fact that d squared y over dx squared is greater than 0. And the reverse is going to be true for a maximum point because the gradient is decreasing. So the rate of change of the gradient is negative. So you've got d squared y over dx squared is less than 0. And those are two absolutely key crucial facts that you're going to be using to answer the question from the previous slide, which is how can we figure out if it's a minimum or a maximum without having to draw the curve. The one that pops up occasionally but much less often is the fact that when you get a point of inflection, you actually find that d squared y over dx squared is equal to 0. So let's go back and have a look at our 2 points and let's just see what's happening with them. So we've got, here's our here's our original function, that's the curve. There's our gradient function. And hopefully by now you'll be realizing that it's absolutely vital that you've been very clear with your notation so you know what relates to what. Let's take the second derivative, so we've got to just differentiate this again. So we're going to take d squared y over dx squared, which is going to be -3 minus 6x. And now we're going to consider what's happening to the rate of change of the gradient at each of our 2 points. So for the first one, we had x was -2. So when x is -2, d squared y over dx squared, let's take -2, put it into here. So we get that. So d squared y over dx squared is 9. It's greater than 0. So based on our statement that we've got up here, because it's a minimum, we know, because it's greater than 0, we know it's a minimum. The flip side of that is that when x is 1, we've got that happening, put 1 in, -9, so therefore it's a maximum.